Everybody's here. Okay. Well, good morning. Welcome to the third day of the summer school. This morning we have the immense pleasure of having Cristopher Eichler to talk to us about superconducting circuits. Cristopher is currently a senior scientist at ETH Zurich in the group of Andreas Wallraff. And very soon he'll be starting his own group at Friedrich-Alexander Universität in Erlangen. Funnily, or as a fun fact, Cristopher holds a double degree in physics and music, where he played the flute as well. So a versatile person. And yes, the floor is yours. We're looking forward to the lecture.
Yeah, thank you very much for the nice introduction and also for having me here in Lausanne at this summer school. I enjoyed the panel discussion yesterday evening and also the follow-up discussions afterwards on the occasion of this apéro very much. And I also look forward to giving this lecture and yeah, also to all the interactions which I'm sure will happen afterwards. So yeah, so this lecture is about superconducting circuits and mostly on how we use these systems for quantum computing. So the superconducting circuit platform has developed into a very versatile, physical system to explore fundamental aspects of quantum optical phenomena, and it's also one of the leading contenders in this endeavor to build quantum computers. What you see here in the background of this slide is one of the very recent multi-qubit quantum processors which we have developed and fabricated and operated at ETH in the Quantum Device Lab. It contains 17 qubits, and we have used this device in order to take an important step towards fault-tolerant quantum computing by demonstrating error correction in a distance 3 surface code. And you're going to hear more about this in today's lecture. So I've chosen, since we have 90 minutes, and this is supposed to be... By the way, is the microphone working properly? Can you hear me well? Is this better? It's probably also better for the audience joining in remotely. Level is okay? People in the back can also hear me well? Okay, there's a number of thumbs up. Good, so then, yeah, we have 90 minutes. This is supposed to be a lecture, so I have decided to devote the first part to giving a basic introduction to superconducting circuits. So we will going to touch upon questions: how do we realize qubits in these systems? How do we operate them? How do we engage? How do we perform readout? How do we initialize them? So this will be pretty much guided by the DiVincenzo criteria, and so we're going to look at how do we satisfy those in these systems. So technology. Okay. And in the Yes, I was just about to tell you about the outline of today's lecture. So part 1 will be about an introduction to superconducting circuits, and part 2 about an example, as I've already mentioned on the title slide, of a state-of-the-art experiment in which we have used 17 qubits to encode a logical qubit and perform quantum error correction in a surface code. So, okay, first question, how do we realize, how do we make qubits based on these superconducting circuits? So the key ingredient is this so-called Josephson tunnel junction, which is a system, a device consisting of two islands of superconducting material, which are separated by a thin insulating barrier through which the charge carriers, which are called Cooper pairs, can tunnel. And if we combine such a tunnel junction, or if we shunt this with a capacitor, we can essentially form a device which acts like an oscillator for the charges which can tunnel back and forth between these islands. And as you can imagine, if charged particles tunnel through this insulating barrier here from one to the other side, then this is also associated with a charge imbalance, which creates an electric field here. So there will be a competition between the tunneling energy and the electrostatic energy. And this gives rise to this oscillating behavior of charges in such a system. So we essentially form an electrical resonator, and because of the nonlinear current phase relation of this Josephson tunnel junction here, this resonator also has a finite nonlinearity. So if we treat this system quantum mechanically, if we write down the corresponding system Hamiltonian, diagonalize it, it turns out that the energy level spectrum, the eigenstates of the system, have a finite unharmonicity, in the sense that the transition frequency between the ground and the first excited state is different from the transition frequency from the first to the second excited state. And for the typical system parameters, this so-called unharmonicity, so the difference between the first and the second transition frequency, is on the order of a few hundred megahertz. And because of this unharmonicity, we can now choose to apply control operations which keep the system in this state manifold spanned by the first two lowest lying states, and without driving transitions into higher excited states. And this is possible because we have this finite unharmonicity. So this is really crucial in order to use these devices as effective two-level systems. But we should keep in mind there exist states higher up in this energy spectrum, and those states we can also make use of. And we will do so, and particularly for performing entangling gates. So one additional very useful feature which we can add to these systems is tunability. So by replacing one of these tunnel junctions here by a pair of tunnel junctions arranged in such a loop geometry, we can now choose to apply a magnetic flux threading this loop. And what then happens is that if the effective Josephson energy or critical current of this junction is varied, and with that also the transition frequency. So we can in situ tune these transition frequencies here, and this can actually done on very fast timescales by making use of on-chip control lines. So then if you look at the typical transition frequencies of these systems, that's on the several gigahertz, on the order of several gigahertz, you will and if we also consider the fairly large size of these objects, it turns out that these systems are very, very well suited in order to be coupled strongly, or they couple quite naturally to radiation in this frequency range. And so this is why this paradigm in which these qubits are coupled to resonators in the microwave frequency range has turned out to be very successful, because these resonator systems can be used as auxiliary devices, for example, to perform readout, as we will also see in a little bit. Okay, that's an overview over the ingredients that we make use of for building these systems. Let's have a closer look at how this actually looks like. Let me give you a bit more of a visual impression of how that looks like in the experiment. So here you see an optical micrograph of one of these qubits fabricated in a planar geometry. So what you see here is, in gray, is a superconducting thin film, which has been structured by making use of lithography techniques and etching techniques in order to remove the thin film, the superconducting thin film, in some of the areas which are shown here as the dark background. So in those areas, we essentially look straight onto the substrate, which in this case is made of silicon. So the dark background is silicon. So you see that by using these etching and lithography techniques, we can now form such islands here, and form a finite, have a finite capacitance to the surrounding ground plane. Yeah? And simply by designing the size of these objects accordingly, we can now fine-tune the capacitance between this central island and the surrounding ground plane to get close to a targeted value. So we can tune the system parameters by design. The central island is then shunted via such a Josephson junction, or a pair of Josephson junction, through the surrounding ground plane in order to form this oscillator, which I have well schematically shown on the previous slide. And as you see, these tunnel junctions, they are typically on the, they are formed here at this crossing point of these horizontal and vertical fingers, and they are typically on the order of 100 nanometer squared. Yeah? So that's the size scale. These qubits can then also be, we can nicely connect to these qubits by making use of on-chip coplanar waveguides, so we can wire them up. And these coplanar waveguides can be used for several purposes. We can use them to form microwave frequency resonators, as you can see here, as these lines which are with these wiggles here, in order to confine them to a smaller region on the chip. So we can also use lines to simply route control and measurement signals, and also as coupling elements to mediate coupling between neighboring qubits. So yes, so this provides a very versatile toolbox. We can lay out all these elements on a chip, design them, and then also choose the parameters according to, let's say, in order to, let's say, design a system that is described by a, let's say, targeted Hamiltonian, if you wish. So this is the system. Let's now understand, how do we perform gates, how do we perform readout in these systems. Let's start with a single qubit control. So the first, or what gets typically done here is the following. So on the chip, we add an open-ended coplanar waveguide. By the way, these coplanar waveguides you can really think of as planar versions of coaxial cables. There's a center conductor with a gap, separated with a gap from the surrounding ground plane, through which we can route microwave signals. And so this open-ended line here will share a finite capacitance to this qubit island, and such that if we apply a control field, with a carrier frequency that is equal or close to the qubit transition frequency, we will essentially induce rotations of the qubit Bloch vector about an axis in the xy plane. Yeah, and the phase of this, or the phase of pulse determines about which exact axis in the xy plane we rotate. Yeah, so by applying these microwave frequency pulses to this line, we can induce rotations about the about an axis in the xy plane. These pulses are typically generated at room temperature with an arbitrary waveform generator and then upconverted into the microwave frequency band, for example, by making use of techniques such as mixing with a local oscillator using IQ mixer. So now there's one subtlety which I typically like to at least highlight or emphasize, and that has to do with the coupling rate between this control line here and the qubit. And this also touches upon a very general aspect that we have to consider when designing such controlled quantum mechanical systems. So obviously, we would, in order to preserve coherence of these systems, we would like to isolate them as much as possible from the environment. On the other hand, if we want to do control operations and readout, we do have to connect them to the outside world, to our control electronics or our measurement electronics. So there seems to be a bit of a contradiction here between isolating the system on the one hand, but also being still able to control these systems. And, and here you see one example of, let's say, a bit of a compromise that we have to make in order to satisfy both these conditions. And so here you see that the coupling rate not only makes this pulse couple to the qubit, which we have to do in order to drive these single qubit rotations, but at the same time it also acts like the control line itself acts like a decay channel. Yeah? So with the same rate, coupling rate, the qubit can now decay into this control line. And therefore, we typically design these lines to have a coupling rate which is much, much smaller than the inverse intrinsic lifetime of the qubit, so to make sure that the lifetime is not limited by the external coupling. Yeah? So it's just something to keep in mind. So this is the single qubit control. I've already pointed out to you that we typically like to work with these tunable qubits, where we can apply a local current through this flux line. So it's another coplanar waveguide, which is grounded in the near vicinity of this loop. It will create a magnetic flux, and this is exactly what we use for in situ tunability. Okay, so this is for the, let's say, single qubit control. What about readout? I've already highlighted to you the usefulness of these cavities or these microwave frequency resonators, and those are exactly the systems which we use as an auxiliary system or a meter, which we controllably couple to the qubit in order to perform what we like to call quantum non-demolition or projective measurements of the state of the qubit. And well, if we would formulate a wish list, yeah, of properties we would like this measurement device to satisfy, then obviously we want these measurements to have high fidelity, so we want to have the capability to assign the correct state with high probability. Readout should be fast. We would like to have a high on-off ratio, in the sense that if we choose not to measure the qubit, then at those times the presence of this auxiliary measurement circuit does not well, induce additional decoherence mechanisms. So this is what we like to call, or what we refer to as a high on-off ratio. Okay, so as I've already mentioned before, before, we make use of microwave frequency cavity in order to perform readout, and this is the techniques that get used here borrow a number of concepts and ideas from cavity quantum electrodynamics, which studies the interaction between matter and at the single particle level. So let's say the generic system that gets studied is a single atom coupled to the light field stored in such a cavity here, and then input and output, or this cavity can then be controlled with an input field, and the light scattered off can be measured. So the circuit equivalent of such a generic cavity QED system can essentially be cast in such an electrical circuit representation, which you show here on the right-hand side. So this is in blue, representing this qubit, which we have learned about before. Then there's a capacitive coupling to a resonator, which we present here as an LC circuit. I will tell you on the next slide how this is often realized by using these coplanar waveguides, and then we can controllably couple it to the external control and measurement line. So the system Hamiltonian for this electrical circuit here essentially consists of three terms. So this is describing the system itself, not yet the coupling to the environment. There's the resonator, there's the qubit with this finite anharmonicity, which we can typically, in a Hamiltonian model, account for by this quartic term here. And then there's a coupling mechanism. Then what gets, which is simply related to the various different capacitances and frequencies in the following way. So then what gets typically done is we perform a rotating wave approximation, assuming that G is much smaller than omega, and a two-level approximation, and this will then simplify this Hamiltonian in the following way, which is known as the Jaynes-Cummings Hamiltonian, which many of you have seen, a resonator field, a qubit, and Jaynes-Cummings coupling between the two. Okay, so what happens if these two modes, the resonator and the qubit, are resonant, so omega r equals omega GE. In this case, the two systems hybridize, so the eigenstates 1G and 0E form these new eigenstates, which are often denoted 1 plus and 1 minus, and they are separated by 2 times the coupling rate G. And one can also measure this experimentally, for example, in such a spectroscopy measurement here, which is where the eigenfrequencies, of where one probes the eigenfrequencies by varying the frequency of a probe tone here, and we're now varying the magnetic flux, threading this loop. One effectively tunes the qubit transition frequency, and then on resonance with the cavity, the splitting here between these two energy states exactly corresponds to twice G, well, divided by 2 times pi. Okay, so this is what happens in the resonant case. What this nicely shows is that one can, in these systems, build devices which have very large coupling strengths on the order of several hundreds of megahertz, and easily reach this strong coupling limit where the coupling rate clearly dominates over the dissipation rates in the system. Now for readout, what we actually want to have is a situation in which there's no resonant coupling between the two systems, but only a dispersive coupling in such a way that the coupling, the effective coupling term, commutes with both the system Hamiltonian of the qubit and the resonator. And this is a property that allows one to do quantum non-demolition measurements. And it turns out that this Hamiltonian here, if we go into this large detuning limit, so if we choose to have the two systems far off detuned, where the detuning is much larger than G, then effectively, by transforming the system Hamiltonian, the effective coupling strength takes the following form. Yeah, so, and I will explain to you how to interpret this coupling term on the next slide, and it will make it very clear why such a coupling term is very useful in order to perform readout. So, yes, so effectively in the corresponding rotating frame and in this dispersive limit, we are left with the following Hamiltonian here. And in this form, yeah, by rewriting this Hamiltonian in this form, you already see what happens. So the resonance frequency of the resonator, omega r times a dagger a, now in addition gets a small frequency shift, which depends on the state of the qubit. Yeah? Because depending on the state of the qubit, sigma z is either plus or minus 1. So depending on the state, the resonance frequency is effectively shifted by either plus or minus chi. Yeah? So if we now were to probe the frequency of this resonator here, which you show here in this plot on in the bottom, then depending on the state of the qubit, yeah, G or E, we find the resonator spectrum, so the transmission spectrum, to be shifted from the bare resonator frequency either by plus or minus 1, depending on the qubit state. And chi, this dispersive shift, is related to the anharmonicity and with, yeah, to good approximation, G squared over delta squared. So how can we make use of this, state dependence of the transmission spectrum or the response, this resonator here, for reading out the state of the qubit? This works in the following way. Imagine we now send a probe tone to the resonator, which has exactly the frequency that corresponds to this intersection point. Then while the amplitude of the field that gets scattered off this resonator is independent of the state of the qubit, it turns out that the phase will be different for the two cases. And so if we measure the amplitude and phase of the signal of the two quadratures, I and Q, then we can resolve a difference, yeah, by essentially, so we essentially get a different signal depending on the qubit state. So one aspect that I also find important to say a few words about is are these coplanar waveguide resonators. So one of the crucial ingredients here is these resonators. Yeah? And there's various ways how we can make such resonators. Let's say, type of resonator that is most widely used are these coplanar waveguide resonators. So let me explain to you, you can think of them. So as I've already pointed out before, these coplanar waveguides, you can think of the planar version of a coaxial cable. There's a center conductor separated by the surrounding ground plane. And if we now fabricate such a coplanar waveguide with a certain length, and at both ends introduce an open end or a capacitor, so a gap in the center conductor, then what happens is that these gaps here essentially enforce boundary conditions, yeah, to the waves which can propagate through this coplanar waveguide. And so what then happens is that these open ends support standing waves in this system with a wavelength lambda, which is set by the length of this coplanar waveguide. And the frequency, the resonance frequency, is then simply related to this wavelength via the phase velocity, which then depends on material properties like the dielectric constant of the substrate and the geometry of this coplanar waveguide. And what is nice about these systems is that simply by adjusting the length of these these coplanar waveguide sections, we can fine-tune or adjust the frequency to reach a target value. So this also offers quite some flexibility. So yes, one maybe detail that I would still like to mention when it comes to readout pertains to the speed of readout, or the ability to perform fast and high fidelity readout without introducing an additional decay channel. So I've already mentioned before this general challenge, to isolate these systems on the one hand from the environment, but at the same time coupling to these systems with rates which are as large as possible, so that we can perform fast operations. And the same, let's say, a consideration we also have to make in the context of readout. And here you see what happens. So the fact that we couple this qubit to a resonator, which is now coupled to a readout line with a decay rate kappa, which we would like to choose to be large, so that we can send in this readout, the microwave frequency radiation, which is used for acquiring information about the state of the qubit as quickly as possible, and also get it out as quickly as possible. We would like to choose this decay rate here as to be large, on the order of several megahertz. But then what happens is that since the qubit couples to the resonator to the this output line, is that there's also an effective decay path for the qubit into the environment via the readout resonator. And it turns out that this decay rate of the qubit scales with kappa times g squared over delta squared, or chi times kappa times chi over alpha. And now you see that there's a bit of a contradiction in the requirements that we would like to satisfy. So at the same time, or we would like to choose kappa large and chi large, but alpha is typically more or less constant. So you see, this seems to be incompatible, but there's a solution. So what one can do is one can include an additional filter circuit called a Purcell filter to suppress qubit decay while allowing for both large kappa and chi. And it turns out that in this case, if we simply add another resonator here in series with the readout resonator, it acts like a filter and strongly suppresses this qubit decay into the measurement line. And I've mentioned it because it turned out to be really the way how we designed our readout circuitry turned out to be key in order to make this error correction experiment turn this into success, and that's why I'm highlighting this technical aspect. So here you see how this typically looks like on a chip. If for a single qubit case, one readout resonator, one Purcell filter, and a qubit. And here in this particular case, the qubit and the Purcell filter and readout resonator are on resonance. So these two modes hybridize. And then there's a weakly coupled input part, a weakly coupled output part for probing the resonator, and with that, the state of the qubit. So let's also get a bit of an idea about the timescales and the fidelities with which one can perform readouts. So for this particular example here, from this paper here in 2017 from our group, everything was optimized for all the parameters, system parameters, to achieve very fast and high fidelity readout for single individual qubits. Just keep that in mind. This is really let's say an example where the readout was or everything was optimized for readout. So what you see here is essentially the time trace of the measurement signal that we acquire in a single run of the experiment. And as you see, there's noise on top of these signals, which is, well, partly due to simply vacuum fluctuations. And in addition to that, classical noise, which is added by the amplification chain that is used in order to bring these measurement signals from the cryogenic system to the room temperature electronics. So this would be the response of the signal that we measure when preparing the qubit in the ground state. When preparing the qubit in the excited state, we see that the response of the resonator, thanks to this dispersive shift, is clearly distinct. And on a time scale on the order of 50 nanoseconds, we can clearly distinguish between these two signals here, even when only considering single instances or single runs of the experiment. Yeah? So in a single instance of an experiment, we can discriminate between ground and excited state with high fidelity. Okay, so this is how a readout gets performed. State of the art in our lab on our devices is that we reach 99% or so readout fidelity when discriminating between the two lowest lying states on the order of, on time scales on the order of a few hundred nanoseconds. So I haven't talked about entangling gates yet, but of course this is a crucial requirement for quantum computing, because if qubits wouldn't talk to each other, well, then all this would be, in a sense, trivial. Yeah? So we have to make qubits interact with each other, talk to each other, so that we can entanglement and eventually compute with a multi-qubit quantum processor. So there's another way of phrasing this is by saying that if we have a multi-qubit register and we want the ability to apply an arbitrary unitary operation on such a register of n qubits, then it turns out that one can decompose such a general unitary into single qubit gates and one entangling gate, which is typically chosen to be the controlled NOT gate. So any unitary you may think of can be decomposed in such a, gate set, universal gate set, and the missing ingredient is this entangling gate. So let's see how we can realize a controlled NOT on a controlled NOT type gate in these systems. Most importantly, two-qubit gates rely on having coupling between multiple qubits. And the simplest way of coupling qubits, two qubits to each other, is by bringing them close to each other so that the two qubit islands share a finite capacitance between them, very analogously to what we have seen in the context of coupling qubits to resonators. And then this coupling rate here is set by is proportional to the coupling capacitance. So by, choosing the distance between these qubits, one can, by design, control this coupling strength. Alternatively, if one wants to, let's say, stretch out or wants to have give a little more room, a bit more space, to each of these qubits individually, in order to also fit all the readout circuitry and the auxiliary control lines on the chip, then one can also make use of coplanar waveguides in order to mediate coupling over larger distances. So here you see on this with the scale bar, that's order millimeter. So by making use of these coplanar waveguide sections, one can then mediate the coupling also over larger distances. And as such, qubits can be spatially separated on the chip. So, but what is important is that the type of coupling, so if you look at this on the Hamiltonian level, then the system Hamiltonian looks exactly the same in these two cases here. So now let's assume that we have the following situation. We have this static coupling with a rate j between the two neighboring qubits, and we allow ourselves to tune the transit frequency of these qubits. Yeah? So those are the two ingredients. That's the situation that we consider here. And now what we want is a controlled NOT type gate. It turns out that it's easier, or given the experimental situation, to perform such a controlled NOT gate, which is essentially controlled X gate in the Z basis. So we apply a controlled Z rather than a controlled X gate. And of course, these two gates are equivalent up to single qubit rotations on the target qubit. So we'll see how we implement a conditional phase gate, a ZZ gate, which takes this matrix form here. For that purpose, we're going to make use of the tunability of these qubits, and the fact that there's also additional non-computational states, and these are supported by these systems. And so we're going to make use of the second excited state of this so-called transmon qubit. So these four states would correspond to the four computational states of this two-qubit system. In addition, so you see that the way how these energies or energy levels are arranged here, that in this situation, the two qubits would be far detuned from each other. Now let's imagine we start with the system in the 1-1 state, and now tune by making use of this in situ tunability, the system into a regime where this 1-1 state becomes resonant with the 2-0 state. Now, what will happen then is that the finite coupling and the fact that these two energy levels are now on resonance will essentially induce Rabi oscillations in this two-state manifold. So the 1-1 state will make an excursion to the 2-0 state, and then come back to the 1-1 state if we choose the interaction time to be proportional to 1/j, the coupling rate between these two. So after a full 2-pi rotation, and this is the most important feature of the way how these quantum mechanical systems interact, we acquire an additional phase factor of e to the I pi, or -1. And if we look at what happens to all the other three computational states, since they, due to the finite anharmonicity, remain off-resonant from any other state, they essentially idle during this time here, so they don't acquire this phase factor. And so this is why only conditioned on having been in the 1-1 state, we acquired this phase factor of -1. So this is how this works. If you want to convince yourself, then here you have a slide, yeah, which shows, let's say, the simplest possible toy model you could consider, which allows you to simulate by simply time evolving an initial state of the system according to the system Hamiltonian, to convince yourself that this indeed leads to this so-called conditional phase factor. Here you also have a few typical parameters, so I really leave this up to you if you want to have another example. Yesterday I understand you had this live session, this hands-on session where you simulated quantum mechanical systems. Here you have another example case that is interesting, yeah, to be maybe studied also with these numerical tools. Yes, so I'm looking at the time, 45 minutes. I would suggest that, and this was also the plan, that I finish the last 2 or 3 slides on part 1. Then we do a 10-minute break, and then, which is also an opportunity for you to maybe come to the front, and we can talk and discuss. You can ask questions, and afterwards we continue with part 2 on this error correction experiment. That sound good to everyone? Okay, then let's continue for another 5 minutes. So I also wanted to tell you a little bit about, because that turns out to be, if you think about this more from the experimental perspective, yeah, you also want to know, well, what's the procedure, yeah, that we have to apply or go through in order to fine-tune all the control parameters or the knobs in the lab that we have at hand at our disposal in order to tune up these gates to do or to perform operations that are close to, let's say, the ideal operations we would like to implement. So let me give you a bit of an impression of such a tune-up procedure in the context of 2-qubit gates. So what you see here is, yeah, okay, let me maybe say one more, yeah. So, okay, so maybe the first thing that we typically want to formulate, yeah, and that probably applies to almost every sort of optimization or tune-up procedure, is we have to formulate conditions which we would like to satisfy, right? Target objectives, if you wish. And okay, what are these objectives here? So after the systems have been interacted, yeah, so we send in a control pulse, the system interacts for a certain amount of time or evolves according to the system dynamics under the influence of this pulse. And after this interaction, we want to satisfy 2 conditions. The first one is we would like to have this phase factor here, this conditional phase factor, to be exactly e to the I pi, yeah? So exactly 180 degrees conditional phase. And we also want to make sure that all the population from the 1-1 state, which has made this excursion to this non-computational state, eventually comes back to the 1-1 state. So these are the 2 conditions. And so now what we can do is we can set up targeted experiments, yeah, or experimental sequences which allow us to measure exactly how well we satisfy these conditions, these 2 conditions. And then we can fine-tune the parameters in order to get as close as possible to the ideal values. So the first measurement here essentially measures how well do we recover the qubit population, yeah? And what is shown here is the population of the 1 state after, as a function of the length of this pulse, yeah, that brings the 2 states, 1-1 and 2-0, into resonance, and as a function of the pulse amplitude. The pulse amplitude essentially adjusts the relative frequency between these 2 states. So here, at this particular amplitude, the 2 states are exactly on resonance, and for this particular time, here at about 75 nanoseconds, all the population has come back into the 1 state. Yeah, so you see that by tuning these 2 parameters, pulse length and pulse amplitude, we can find pulse parameters for which all the population has been recovered. We also want to satisfy this condition of having exactly a conditional phase of pi, and for this one typically performs a Ramsey experiment on one of the qubits with and without having applied a pi pulse on the other qubit before performing this, applying this flux pulse. And so by comparing the phase acquired by this qubit 7 here with and without the pi pulse, we the difference between these two is essentially this conditional phase. So by simply doing these two Ramsey experiments and subtracting the two phases from each other, one can map out this conditional phase here, which is plotted here again along this line here in parameter space, and as such we can identify pulse parameters, amplitude and time, marked here as by this green spot, which satisfy both these conditions. In practice, yeah, there's typically, this is an iterative procedure, yeah, so one can iterate between these two types of measurements, fine-tune the parameters, and then eventually perform gate characterization by performing tomography, belt state tomography, process tomography, and also benchmarking, randomized benchmarking, or cross-entropy benchmarking. So this is how this works. There's also a slide on some of the properties of these phase gates. I will not touch upon that. I will just tell you also a little bit about the experimental setup, again, to give you a visual impression. So here you see how we connect these devices after fabricating them into a printed circuit board to be able to connectorize them to these coaxial cables. And all this sample package here is then thermalized to the base plate of a dilution refrigerator. We cool it down to 10 millikelvins. That guarantees or ensures that the system is ideally starting in the ground state, yeah, because the thermal energy is much larger than the no, this should be interesting. So h bar omega is much larger than kBt. I've probably shown this slide a couple of times without recognizing it. Today I'm recognizing it, so kBt is smaller than h bar omega. So that's why we use this cryostat. So we initialize the system by cooling. Yeah, many of you have possibly also seen labs, superconducting circuit labs. There's a bunch of control electronics made use of, which are then connected to the devices in the cryostat and to orchestrate all the control signals that are sent down to these devices. With this, I finished part one. I would maybe still give you the opportunity to ask questions, either in plenum, or you can also come to the front and we can discuss in person. And I would suggest we continue in about 10 minutes. Okay. Okay. New battery. I think that sounds better now. Okay. So I suppose that people which have possibly joined in remotely will probably appreciate that now the microphone is also working. So, okay, welcome back to the second part of this lecture. Which be about this recent experiments on realizing quantum error correction in a distance 3 surface code, which well, made use of the 17-qubit device, which you have already seen on the title slide. Let me first of all greatly acknowledge the team of people which have contributed to this project over the past year. So this was really a very long-term effort which has led to this result. And we also had very nice theory collaborations with Markus Müller, who is also in the audience today, and with Alexandre Blaise group, especially in the at the end of the project, when we were close to reaching the finish line. So maybe to connect this or to motivate a bit or provide some context, I guess in yesterday's panel discussion, most of you probably had attended that as well. I think we touched upon two topics. Or one of the questions was asked, okay, what about the feasibility of the current devices in the NISQ era in order to, let's say, perform computations which are beyond the read, say, classical computers, and then, okay, what is actually required in order to eventually do fault-tolerant quantum computing, for which we know what the possible applications are. Yeah, and I think this first application in this NISQ era, it's a lot less clear, what potential applications might be, and how what the computational power of these devices might be. But what is very clear is that once we are able to perform close to error-free computations on quantum computers, then we will have access to, for example, performing quantum chemistry simulations, or performing a Shor algorithm, to give a few examples. So this is why there's, and this will likely still be a long-term effort, there's a big need for performing quantum error-corrected or building quantum error-corrected computers. So, well, we are still at the very beginning of where we just start to be able to have hardware available in which we can logically encode quantum information. And so to tell you, okay, so what is the basic idea behind quantum error correction? So the main ingredient here is that is redundancy. So the idea is that one encodes quantum information in a larger dimensional Hilbert space, and so that while performing computations on these logically encoded qubits, one can also perform certain types of measurements, measure certain correlations, which tell us about errors as they occur, and this information can then be used in order to find a corrective action and, compensate for these errors or correct these errors. Yeah, so that's the basic idea. So redundancy. Let's see how such a redundant encoding can help in order to detect errors and eventually correct for them based on a simple example of a so-called 3-qubit bit flip code. So imagine that rather than storing one logical bit of information in just one physical qubit or data qubit, we now choose to use 3 data qubits to encode one logical bit. And the two code words could be chosen to be 0, 0, 0 and 1, 1, 1. Yeah, so we have chosen 2 out of 8 basis states in this 8-dimensional Hilbert space as the 2 logical states. And so now let's see how such an encoding can help us in order to identify errors, yeah? In this case, bit flip errors. So if you look at the case where the third of these data qubit has undergone a bit flip error. Yeah? So this would take an initial state, alpha logical 0 plus beta logical 1, to the following state, yeah? Where the last of these 3 data qubit bits has been inverted. Yeah? The challenge is now to detect this error event without collapsing the entire wave function. Yeah? So we would like to be able to find out about this error without knowing or without learning about whether we are in logical 0 or logical 1. Yeah? So without acquiring logical information. Yeah? And so obviously, if we were to choose to measure these data qubits independently one by one, then this would collapse the entire wave function and destroy the logical information. So we are not allowed to do that. But what we can do is we can measure pairwise parity correlations. So we can ask questions such as, is the sum of the first 2 bits, is it even or is it odd? Yeah? So this is a question that we are allowed to ask. Yeah? And well, more formally, asking that question corresponds to measuring the following observable, so products of Pauli Z operators. Yeah? If we measure this observable here, so which is called a parity operator, then the outcome is either plus or minus 1, and plus 1 in the case that the sum of the first 2 bits is even. So in this particular example here, the answer would indeed be even because 0 plus 0 is even, 1 plus 1 is also even. So in this subspace spanned by the first 2 data qubits, the parity is even. Now, if we were to ask the same question for the second and third data qubit pair, then, well, the answer would be odd, yeah, because the third qubit has changed its value, yeah, so because the third qubit has flipped. And so this means that we know that there must have been, relative to the, let's say, ideally encoded state, an error, a bit flip must have occurred. And from these 2 pieces of information, the first parity value being even, the third one being odd, one can unambiguously reconstruct on which of the 3 data qubits this bit flip must have occurred. So you see that these parity checks allow us to both preserve the logical information and to acquire information about these bit flip errors. Yeah? So the question is then how to measure parity. Okay, so this was a slide that I also wanted to show actually before, to put this a bit into context. So this is a slide showing other experimental work in the context of quantum error correction, but maybe to keep the flow, I will not discuss this now, and maybe come back to it afterwards. So I was just about to ask this question: how do we now measure parity correlations between multiple qubits? One way to do so is to make use of additional helper qubits, auxiliary qubits, how they are often called. Here, the qubit marked in green. Yeah? So let's imagine we have these two data qubits, D1, D2, of which we would like to measure this parity correlation, so the product of Pauli Z operators. One way to do so is to simply perform controlled NOT operations with the ancillary qubits, which then really acts like a counter, if you wish, for the number of excitations in these two data qubits modulo 2. Let me maybe make this a bit more explicit. Imagine the two data qubits start out both in the 0 state. In this case, both these controlled NOT gates wouldn't do anything to the ancillary qubit, so the ancillary qubit would just remain in the ground state. Same if the two data qubits start out in the 1 state, both these controlled NOT gates will perform a bit flip on X gate on the ancillary qubit. So it's going to be flipped once, it's going to be flipped twice, so it will also go back into the 0 state. So importantly, executing this quantum circuit followed by a measurement of the auxiliary qubit will not distinguish between the 1, 1 and the 0, 0 data qubit state. So there is some erasure of, let's say, information within this even parity subspace. Yeah? So it only distinguishes, we could do the same exercise now also for the odd states, or the states in the odd parity subspace, and then see that the ancillary qubit would end up being in the 1 state. So this circuit here distinguishes between even and odd, but not between states within these two parity subspaces. And that's very important, yeah, because this turns out to also the fact that we do not distinguish between states in these degenerate subspaces allows one to essentially create entanglement by parity measurement. Yeah, and this is, for example, also the reason why by performing these parity checks, we essentially create entanglement between the data qubits in doing so. So, okay, so now let's also, in order to get a bit of a clearer idea also about the connectivity and some of the geometric aspects, let's now think about, for our 3-qubit bit flip code example, what kind of requirements this would impose in terms of connectivity. Yeah, so obviously, if we want to perform a C-NOT gate between each of the data qubits and the ancilla, we need a connection, a coupling between this ancilla and the two data qubits we would like to measure the parity of. The same if I want to perform a parity measurement on the second and third data qubit, we could make use of an additional auxiliary qubit coupled to these two qubits. So that's kind of the connectivity or the layout of qubits that we would need in order to perform this experiment. So, well, now this was a simple example to illustrate the basic idea behind parity check-assisted error detection and eventually correction. This code is capable of correcting exactly one single bit flip, but it does, for example, not correct for phase errors, phase flip errors, yeah? Z errors, Pauli Z errors. So for the, obviously, at the end of the day, we would like to be able to correct both X and Z type errors, Pauli errors, which turns out to be sufficient in order to correct any error. And for that purpose, we need a more sophisticated code. This will now very naturally bring us to the surface code, yeah? Because this turns out to be capable of both correcting X and Z type errors, and also it's scalable in the sense that we can increase the size of the encoding and then also be able to correct more than a single error. So the basic idea is very similar to what I've just shown to you. So we have data qubits which encode the logical information. We have additional helper qubits which are connected to these data qubits to perform controlled knot entangling gates. But now we simply extend this idea by now having data qubits arranged in such a two-dimensional lattice, and having now ancillary qubits not only measuring parity in the Z basis, but also half of the ancillary qubits measuring parity in the X basis. And measuring parity in the X basis, as you can already imagine, will then tell us about errors which have occurred in the transversal basis, so about Z errors. Yeah? So the combination of having X and Z type parity information allows one to learn about X and Z type or Z and X type errors. Yeah? So that's the basic idea. Also, one difference compared to the written code is that now these parity operators, if you look at one of these ancillary qubits, it connects to 4 data qubits, yeah, so not only 2, and so this is why these parity operators are now of higher weight, and so the corresponding quantum circuit that would map this parity onto the corresponding ancillary qubit now also contains 4 rather than 2 controlled NOT gates. Yeah, so we measure now products of 4Z or 4X type Pauli operators. Okay, what is the big promise here? So the big promise of quantum error correction is that once we manage to perform all these individual operations, gates, measurement operations, with the performance or with the fidelity that is above a certain threshold, then by increasing the size of this code, yeah, the size of the code would correspond to this distance d, so it's the number of data qubits in one such row. So in this example, it would be 5. So by increasing the size of the code d, one can exponentially suppress the probability of having an error on the logically encoded qubit. Yeah? And well, this is great. But as I've said, yeah, so it relies on making P, so the error probability on the physical level to be sufficiently small so that it becomes below this threshold value, which for the surface code is on the order of 1% or so. Yeah, so that's why making 2-qubit gates, yeah, beyond this 99% level is an important step that has to be reached. Okay, let me also tell you a little bit about earlier work on this surface code experiment. So obviously the smallest viable instance or non-trivial instance of a surface code you could imagine would be a distance 2 code. A code where there's 4 data qubits arranged in such a plaquette and 3 ancillary qubits. So for this code, it turns out that one can detect single errors, but whenever an error occurs, there's no way of, let's say, unambiguously finding out which error has occurred. And then this is why a distance 2 code can detect but not correct errors. So this is why the smallest viable instance for doing error correction to first order has distance 3. And this is why it was such an important step for us, yeah, to go from devices, yeah, which contain 7 qubits to devices which have 17 qubits, so, to perform or to realize this distance 3 code. And well, I mean, this is all work that studied this distance 2 code, and you see this is also very recent. And yeah, we are very excited that we have now yeah, managed to realize this distance 3 code, yeah, which essentially looks as follows. So there's this 3 by 3 grid or lattice of data qubits, and then 8 parity operators. So a note about terminology. So far I've talked about parity operators. In the context of these surface codes, they are typically referred to as the stabilizers of the code. So in the following, I will typically use the term stabilizer, but it's exactly the same, let's say, mathematical object, yeah, which I've called parity operator on the previous slides. So just to avoid confusion, and yeah, so a few properties of this code. So there's 4 Z-type stabilizers, or parity operators, 4 X-type stabilizers, and the distance of the code is 3. Logical operators can be defined as rows and columns of data qubits, and yeah, that's the distance 3 surface code. All right, so that's the concept, but of course, as an experimentalist, we had to design and fabricate and develop devices, which turned out to be a major effort. It contains 17 qubits, but in addition to that, all these coupling elements, readout resonators. So that was a long process, yeah, to get all the individual constituent elements to work. Also, parameters close to target, and yeah, I think at the end of the day, we managed to get a device with the following properties. So here you see in yellow these 17 qubits, 9 of which are act like data qubits, 8 of which act like ancillary qubits. Each of them has these charge and flux control lines shown here in pink and green, and the single qubit gates can be performed with a fidelity above 99% across the entire device. This is partially thanks to the good coherence times. Yeah, so the average T1 and T2 times are both above 30 microseconds. It's yeah, so which is were quite good numbers also for us at the time, and yeah, and given the complexity of the device, this was by far not obvious. 2-qubit gate errors also across the entire device, and remember there is in total 24 connections between these 17 qubits, so 24 2-qubit gates. Average gate error is 1.5%. Then I already highlighted the importance of readout. Let me maybe re-emphasize why readout is so important in the context of quantum error correction. So what we want is the ability to perform measurements on the auxiliary qubits without perturbing the state of the data qubits. Yeah? So we want to have the ability to perform these mid-circuit measurements on a subset of qubits. Yeah? So you can imagine that depending on, if there's all sorts of things that can go wrong in principle, which could, for example, induce dephasing on neighboring qubits when choosing to measure one of the ancillary qubits. Yeah? And it turns out that the fact that we make use of these Purcell filters in each one of these readout circuits not only protects the qubit from decaying into the environment, but it also protects the readout resonators from off-resonant driving, and as such strongly suppresses readout crosstalk or cross-measurement-induced dephasing. Yeah, it's a bit of a, again, a technical detail, but which turned out to be very important because it really allows us to perform readout on the ancillary qubits without perturbing the data qubits, or with little disturbance on the data qubits. So readout errors are shown here. If we discriminate between two states, it's below 1%. If we also choose to discriminate between the second excited state to detect leakage events, it's on the 2% level. Let me also say a few words about the device architecture, so which I also find very important. We typically lay out the qubits. They have a, let's say, there's a spatial aspect to it. Yeah, so we have to figure out how to best distribute these elements on the chip. But then we also have to distribute these various different elements also in the frequency space. Yeah, so because with each of these elements we associate a characteristic frequency. Yeah? So each qubit has a transition frequency, each readout resonator has a frequency, and so this is the frequency configuration that we had chosen for this device. So what we have done is the following. So we have made use of asymmetric squids, so in these pairs of junctions through which we can then apply magnetic flux for tuning the frequency. We choose the Josephson junctions to be of slightly different size. Yeah, and as such, there's the tunability of these qubits has an so-called upper and lower sweet spot, or lower minimum and a local minimum and local maximum. Yeah, and these are frequencies at which the qubits are first-order insensitive to magnetic flux noise. And we've designed these qubits to have these upper and lower sweet spot to be in the 4 and 6 gigahertz band, and all the data qubits are idling at their corresponding lower frequency sweet spot, and the ancillary qubits in the 6 gigahertz band at the upper frequency sweet spot. The vertical bars indicate the range of tunability, and so you see that we can now tune the data qubits up in frequency and the ancillary qubits down in frequency. So what we can do to implement gates is we can tune pairs of qubits towards each other to an intermediate frequency where they interact. Yeah? And as such, we perform 2-qubit gates. And this turns out to, at least for the 17-qubit geometry, allow one to parallelize some of the gates and also avoid, for example, the coupling to spectator qubits during the while performing these gates. That's also the reason why the detuning between these bands is chosen to be fairly large, on the 2 gigahertz level. Okay, so I've said enough about readout. Let's now turn to the device performance and by looking at the distribution of the performance. So I've already commented here on the average numbers. What I also wanted to highlight is that while there is some spread in performance, yeah, so if you look, for example, at the 2-qubit gates, yeah, so some of the gates perform better than others, the distribution is still relatively narrow. Yeah, so there is no clear outliers. Yeah, there is no individual operations which perform significantly worse than all others. So across the entire device, performance is reasonably good, yeah, and the distribution of performance is sufficiently narrow. Yeah, and that's also an important aspect in all this. It's not only about the average performance, but of course also that we avoid that some of the gates don't work at all, or with very poor performance. Yeah, and that it turns out not to be the case here. So we can then move on and characterize these stabilizers. Yeah? So we, by preparing the data qubits in one of the possible basis states, yeah? And then simply run this stabilizer circuit, yeah? So which is the sequence of controlled NOT gates, which maps the stabilizer onto the corresponding ancilla, and then reading out the ancilla. We can repeat this, average, and then we obtain the average stabilizer outcome. What we would expect is that if the data qubits are prepared in an even parity state, the stabilizer value is plus, odd data qubit states -1. So, so that's what we would ideally expect. In the colored bars show how well it works in the experiment. You see that it works, it's in it works to a level where weight 2 stabilizers have about 4% average error and weight 4 stabilizers 8%. And given the complexity of the entire circuit, so what you have to remember is weight 4 stabilizers contain a sequence of 4 ZZ gates, additional single qubit gates, and readout of the ancillary qubit. And this entire quantum circuit has an infidelity of an error for misclassifying the stabilizer of about 8%. We also find good agreement with master equation simulations, which indicates that when accounting for the known errors on our devices, we can explain the majority of the errors that we also observe in these stabilizer experiments. Okay, we can now move on and put everything together and run the surface code experiment by essentially measuring all the 8 stabilizers in the following parallelized fashion. So here you see the tableau, or the quantum circuit, which is used in order to perform these 8 stabilizer measurements in about 1 microsecond. Yeah? And in order to keep the duration of this stabilizer or this quantum error correction cycle as short as 1.1 microsecond, one makes use of this pipeline technique, which has been developed in Leo Di Carlo's group. You can find more information about it in 2007 in this paper here. The basic idea is that while mapping the parity information of one type of stabilizers onto the corresponding ancillars, so for example, the entangling gates between data qubits and the X type ancillary qubits, one already or simultaneously performs the measurement of the Z-type ancillars. Yeah? And since the duration of measurement is about the same as the duration of 4 of these controlled Z gates, this just matches up time-wise quite nicely. So this pipelining, as I've said, results in a cycle duration of 1 microsecond. And now what one can do is we can initialize the state of the qubit, of the data qubits in a product state, and then perform 1 round of these stabilizer measurements in order to prepare a logical state, or in order to initialize a logical state. And then we can continue to repeat these quantum error correction cycles and monitor how well we can preserve this initialized logical cycle over the many, many cycles of these stabilizer checks. Yeah, so that's what we've done, and let me tell you more about it. So the first thing that we can do is we can, but maybe in the interest of time, I maybe skip the discussion of that, so that would have been about the logical state characterization. Yeah, so I think it's time to wrap up. Yeah, and move straight to the logical lifetime measurement. Okay, so yeah, as I've said, the idea of the experiment is 1 cycle of parity checks is performed in order to initialize a logical state, and then additional cycles are performed, which then tell us about errors, yeah, which they essentially, which the information of which can be used in order to apply at the end of the experimental sequence a corrective action if needed. Let me tell you how this works. So how these parity or stabilizer measurements can tell us about errors. So imagine that we start out in cycle 1 with a situation where all the ancillary qubits yield a value 0, which corresponds to stabilizer or parity +1. Yeah? But then, let's say from cycle 1 to cycle 2, the data qubit shown here, the middle one in this leftmost column, might have flipped, which would trigger the parity or the stabilizer of the connected Z-type stabilizers to change their value. So what you can read off from this example is that, well, whenever an error occurs, it leads to a change of the stabilizer value. Yeah? And this is what we would refer to as a detection event, yeah, or syndrome. Yeah? So in mathematical terms, what we do is we compare the stabilizer value of subsequent cycles. Yeah? So here, cycle m-1 with cycle m. And if they are different, sigma, the syndrome element, would be 1. If they are the same, the syndrome element would be 0. So whenever this syndrome element takes value 1, this signals an error event. Whenever it's 0, well, we would expect that no error has occurred. So this is also the reason why the average value of sigma, the syndrome element, if we average over many, many repetitions of the experiment, also tells us about how likely it is to have an error event happening. So if this number is small, that tells us that errors are rare events, yeah? So that errors only happen very rarely. Yeah? And this is a requirement in order for error correction to work, yeah? Because only then, especially in a code with low distance, because only if errors are rare events, we can reconstruct the most likely error from these syndromes with low ambiguity. So let's see what the value of sigma is in our experiments when averaging over many, many runs and all the different ancillas on the chip. What we find is sigma corresponds to 14%, which is indeed substantially smaller than 1. And this, well, you could argue, gives us hope that indeed reconstruction of the most likely error with low ambiguity should indeed be possible. There's a lot more to be said about this. You can ask me afterwards, but I will not discuss it in more detail here, but rather straight show you the most important result. So, which is this quantum memory experiment, or the state preservation experiment. So where one monitors how does an initial eigenstate of the logical Z operator, how does that evolve over time or over many cycles of quantum error correction. And so what gets done here is we perform n QEC cycles, which where n goes up to 16, and then measure all these syndromes of stabilizer values in each round, and then by using a decoding in post-processing on the data that we acquire, we can then apply a corrective action on the final measurement outcome of the data qubits, and then compute the value of logical Z. Yeah, we can then average over many repetitions to then essentially measure this lifetime plot of the evolution of this initial logical state over time. What we find is a lifetime on the order of 16, 17 microseconds, which, and I think this is most important, is much longer than the cycle time. Yeah? Why is this important, or an important metric? Because if we now translate this into an error per cycle, which is essentially the ratio between the cycle time and the logical lifetime, we find an error per cycle on the order of only 3%. Yeah? So what that essentially shows is that, well, it's not only about the logical lifetime, but it's the logical lifetime in comparison to the cycle time, Because if you have the same logical lifetime, but you can increase the speed with which you can perform these QEC cycles by a factor of 10, this is equally good. Yeah, so it's really about the ratio between these two that matters, the logical error per cycle. One can also put that into relation to the average two-qubit gate error on this device, yeah, which is 1.5%, so there's about a factor of 2 difference. The fact that I haven't explicitly mentioned it, but there's also good agreement between numerical simulations and the performance that we find in the experiment, which suggests that one could use these simulations to also project performance. Let's say if we were to, let's say, improve the physical error rates by, let's say, a constant factor x, and what this suggests is that, well, maybe a factor 2 or so of improvement would possibly get us to a point where the logical error per cycle starts to be lower than the error on the physical two-qubit gates on this chip, which is the worst performing operation on the physical level. Okay. Also worth mentioning is that these 3% error per cycle is also comparable to the predicted logical error per cycle at the threshold as estimated in this paper here by Austin Fowler and co-workers, which also suggests that, well, the performance is maybe not quite at the threshold yet, but also not orders of magnitude away. Yeah, so with, let's say, moderate improvements, yeah, one should be able to get to the threshold. Okay, with this I maybe wrap up. I'm already 5 minutes over time. So I've told you about this, after giving you an introduction to superconducting circuits, about this repeated quantum error correction in a distance 3 surface code. We found a logical error per cycle of only 3%, which suggests that break even with the two-qubit gate performance is within reach and possibly also reaching the threshold. There's a number of interesting, we have, as I've said, just at the beginning of a very interesting journey where we start to perform experiments at the logical level. Moving forward, one would of course like to increase code distance, also perform logical operations, and yeah, as I said, the future is bright and interesting. So as I've already mentioned yesterday, my journey will soon continue at the Friedrich-Alexander University in Erlangen, and so I will start a superconducting circuit lab there 1st of September, and yeah, if you're interested to join a newly established superconducting circuit team, contact me. I've also recently announced yeah, PhD positions. We have a number of openings. With that, let me also thank the entire team at the Quantum Device Lab, and which has been a great fortune to work with over the past years, and also thank you for attention.
So, first of all, thank you very much. Some chocolate for you. We have time for one short question, and then we will proceed to the coffee break.
Thanks so much for this wonderful talk. My, I think, most pressing question is, what would be the next step forward to reach the quantum error correcting code that can actually achieve break even? Is it like shorter cycle time? Is it improvement in the physical qubit? What would you say?
Yeah. So I think as I've already mentioned, and this is also supported by these simulations, the worst performing operation at the physical level is currently the two-qubit gate still. But of course, one could also benefit from even speeding up the error correction cycle by making it even faster. which could benefit not only from faster gates, but also from faster readout. Yeah? Because if you look at the time required for readout, it's still on the order of several hundreds of nanoseconds. And of course, one could also benefit from possibly further parallelizing the way how these different operations can be performed. Yeah? For example, in this Google experiment on the repetition code, one of the nice features of the experiment was that they could highly parallelize the 2-qubit gates. However, the readout was slower, so at the end of the day, it was also not very fast, but at least the 2-qubit gate time was very, very short. So speed is clearly one aspect. And then, gate fidelity, 2-qubit gate fidelity. I haven't had time to touch upon it, but a very active field of research is now also on tunable coupler-assisted gates. So here we have static couplers, simply because it's easier to realize. There's fewer Josephson junctions. There's already 17 qubits, yeah, which is already a very complex device. But looking forward into the future, I guess that the trend goes to tunable coupler-assisted 2-qubit gates, because that can help one to also increase on-off ratios, make faster gates, and with that higher fidelity gates. But yeah, it's also a challenge, yeah, to do that, to realize that.
Okay, with this, let's thank again Christopher, and we convene. Wait. We convene at 5 past, maybe 7 past, so there's a small coffee break, but not too long. And he is with us the whole afternoon, is that correct? Yes, so feel free to ask him any questions.